All right.
When are we getting this summer ready for?
We'll have Mr. Hill come in maybe the last week of school. Okay. Mean value theorem versus Rolle's theorem. Essentially, Rolle's theorem is just a more specific version of mean value. So with Rolle's theorem, it says the f of A has to equal f of B in your interval from A to B. So in other words, they're at the same level and the average rate of change is 0. So when you kind of look at if I just do a random function like this.
So he literally just took his idea and put his name on it.
What?
This is the same thing.
It is. So f of A and f of B are at the same level, so your average rate of change is just 0. So, and the same stipulations, f of x has to be continuous and differentiable on the interval from A to B, then there exists at least one number c in that interval such that f prime of c equals 0. It is just a more specific version of the mean value theorem. That's it. Nothing to it. So, really, because the average rate of change is 0, it's going to give us the location of relative maxes and relative mins. It's going to feel very similar to what we were doing the other day, which is setting the derivative equal to 0. But you just have to make sure it applies by checking f of A, checking f of B, making sure that average rate of change is 0. So find the two x-intercepts of the function. Okay, we'll do that first. So pretty easy. X equals 0, x equals 3. And show that f prime of x equals 0 at some point between these x-intercepts. So our points are 0, 0, and 3, 0. Our slope is 0 between them, obviously. We need to show that the derivative equals 0 somewhere in between. So our A to B interval is 0 to 3 here. I'm going to write interval next to this because when you have points floating around next to intervals, obviously the notation is the same, and so that can get confusing. But we're just going to find our derivative, which I'm going to first rewrite the original and distribute that x so that my derivative will be pretty straightforward. Set it equal to 0. 2x equals 3. Divide by 2. X equals 3 halves. Confirm that that's in your interval. Yes. So we showed it. Go ahead and do part B on your own. Conceptual piece here. I'm going to graph this on the calculator and kind of explain and show what we did, the whole process. So I'm only going to look at the window from 0 to 1 because that's what our or negative 1 to 0 rather, because that's what our x-intercepts were. So there's my function, window, negative 1 to 0. We'll see if negative 5 to 5 is good enough for the moment. But here's your graph. So we know that Rolle's theorem works because the interval starts and ends at the same value. So the average rate of change is 0. So we take our derivative and set it equal to 0. And we're looking for the place in between this interval where, and we can kind of see it up here, where we have an instantaneous rate of change of 0. And we found it to be at negative 2/3. So if we, I don't know how we would do this, but second trace and just looked at negative 2/3, you would see that that would be kind of at the top of that peak right there. One of the, obviously finding the derivative, you got to make sure you're good and clean with that. But then solving, oh, I guess I didn't cross multiply. I just got rid of the fraction and multiplied by that on both sides. But same thing would have happened. 3 times 2 is 6. The big thing here not to forget is that root x plus 1 times root x plus 1 is x plus 1, which is all well and good, and you know that, but you have to keep it in parentheses because it's a binomial, and that 6 has to be distributed. Okay? Any questions on that? Okay. Determining whether Rolle's theorem can be applied on the interval. So the first thing we need to look at are the endpoints, 1 something and 4 something. When you plug in 1, you get 1 minus 5, which is negative 4 plus 4 is 0. When you plug in 4, you get 16 minus 20, which is negative 4 plus 4, which is 0. So as long as those y coordinates are the same, and your average rate of change between those two endpoints is 0, we're good to go. So is it differentiable and continuous in that interval? Of course, because it's a quadratic. We've got the endpoints working out okay. Then find all the x values in the interval. So we're just going to take our derivative again and set it equal to 0. So x is going to equal 5/2, and just confirm that that's in your interval. Done. 2.5 is between 1 and 4. So I'm immediately nervous because it's an absolute value. We can't find the derivative of an absolute value function generically, which hopefully is not a big deal because where is this not differentiable? At 3, okay? This is an absolute value parent graph that's been shifted to the right 3 units, flipped upside down, and shifted up 3. This is the same one that was on our notes or something the other day. So at 3, it's not differentiable. That's in your interval. So this mean value theorem does not apply. See, if you didn't realize that and you plugged in 0, you'd get 0, 0. You plugged in 6, you would get 6, 0. It would seem to work otherwise, right? The slope between those would be 0. You'd think, okay, it applies. So you'd have to take the derivative and set it equal to 0. And we can just see by looking at it, the slope never equals 0 on this function. So you'd have trouble, you'd have trouble finding the derivative generically because we can't do that with absolute values yet. And then, obviously, even if you could, it would never equal 0. Okie doke, so does not apply because f of x not differentiable along interval. Okie doke. Okay, so on this next one, we're looking between the interval of 0 to 2 pi. So cosine of x is definitely continuous and differentiable. Look at your endpoints. Cosine of 0 is 1. Cosine of 2 pi is 1 as well. Average rate of change, obviously, is 0 because they're starting at a level of 1 and ending at a level of 1. Take your derivative, negative sine of x, set it equal to 0, and solve. So when does your sine x equal 0 along the interval from 0 to 2 pi? Just pi. Right? It also equals 0 at 0 and at 2 pi, but we're not including endpoints in our solution, so just at pi. Okie doke.
Why wouldn't we include that? Because there's
Just it's a finicky thing with the definition. It has to be in the interval with parentheses A to B. So between A and B, not including the endpoints. It's just by nature of the definition. Secant. All right. Negative pi over 4 and pi over 4 have to be plugged in just to confirm. Secant is not a continuous function, right? Quick review. Secant is the flip of cosine. So if I look at a cosine curve from negative pi over 4, which is here, to positive pi over 4, right? That's the cosine curve. The secant curve would have an asymptote here and an asymptote here and would reflect up. So this is negative pi over 2 and positive pi over 2. So between negative pi over 4, which is here, and positive pi over 4, which is here, we're all good, right? Continuous and differentiable just in this little stretch here. So that's fine. You can obviously already see from the graph that it's symmetrical, right, to the y-axis. But if you want to find the values just for the sake of doing it, the cosine of pi over 4 is root 2 over 2. So the secant of that would be 2 over root 2. And same thing with the negative pi over 4. That's a fourth quadrant, so cosine is still positive root 2 over 2, so we reciprocate still. So we're good there. You could verify mentally that that was applying, obviously, via the graph. But our derivative of secant is secant tan. Set that equal to 0. We're just going to tee this up. So we're looking for where the secant x equals 0 and where the tangent of x equals 0 within the interval of negative pi over 4 to positive pi over 4. So if it helps you, like it helps me, I'm going to think of the unit circle. Between negative pi over 4 and positive pi over 4, we'll start with tangent because it's easier. When does the tangent equal 0? At 0. And when does the secant equal 0? Secant is 1 over cosine of x. Never. So you only have one answer. Good? Any questions? And on our last one, the ordering for and transportation cost C for components, we have a function where C is measured in thousands of dollars and X is the order size in hundreds. So they want to verify that C of 3 is equal to C of 6. So the cost when you buy, the cost when you order and transport 300 items is the same as when you buy and transport, order and transport 600 items. So we're just going to plug that in. C of 3 equals 10 times 1/3 plus 3 over 6, which is 3 6 plus 2 6, 5 6. 56 for C of 3. C of 6, 10, 1 6 plus 6 over 9 is 10 times, oh boy, those both go into 18, so 3 18ths and 12 18ths is 15 18ths, which reduces to 5 6, 56. So we verified that. And then just find the order size. So somewhere between 3 and 6, we have to set the derivative equal to 0. So C prime of x equals 10 times, I don't know if I want to do it this way, because I'm going to have a quotient rule in there. I'm going to distribute the 10 in the original. That's just my personal preference. I'm also going to rewrite the original as 10x to the negative first on that first term anyway. So the derivative power rule, negative 10x to the negative second on the first term, plus quotient rule on the second fraction. Bottom times derivative of the top minus top times derivative of the bottom is just 1 all over the bottom squared. I'm going to clean that up. Negative 10 over x squared. Let's see, my numerator is going to be 10x plus 30 minus 10x, so just 30. And I want to set this equal to 0. I'm going to add that 10 over, that 10 fraction. Cross multiply. I'm going to square out this x plus 3 while I'm at it. X squared plus 6x plus 9. So 30x squared equals 10x squared plus 60x plus 90. Subtract my 30x squared over. Negative 20x squared plus 60x plus 90. Divide out of 10. This is fun, isn't it? And factor. I don't like this. Can I switch my signs? 2x squared minus 6x minus 9. Nine and 1, 1 and 9, 3 and 3. What's happening? Is it factorable? Quadratic formula, 6 plus or minus the square root of b squared minus 4ac all over 4. 36 times 2 is 72 plus the 36, 108. 6 plus or minus the square root of 108 over 4. The minus 1 we're going to ditch because it'd be a negative number. The plus 1 is going to be our answer. A lot of algebra at the end there.